Hello, welcome to Mechan 2040 Solid Mechanics. I am Globas Wu. I am a Mechan Year 3 student. So today I'm going to introduce you the second tutorial, which is about the analysis of axially loaded members. One precaution is that for this video, there will be intensive mathematical manipulations. So if you are not good at math, try to follow me, and if you really cannot follow, you should try to get some help from maybe math support center or your professors. The tutorial today includes a very quick review of what we have learned in the previous chapters. Also, we will discuss the lecture content very quickly, so those three parts are all about thermal effect, statically indeterminate problems, and design considerations. For those three sections, the formula involved is quite few, so the tutorial agenda today is as follows. We will firstly have a very quick review on what we have learned in the last tutorial. Besides, we will go through 2.1 to 2.3 very quickly about the thermal effect, the statically indeterminate problems, and the design consideration of safety. So in those three sections, there are not many formula. So even for the entire tutorial today, we don't have many formulas. However, we will discuss the examples intensively because for this chapter, rather than talking about the formula, the examples are more important for you to understand what we are actually talking about. Besides, we will discuss about the stresses in the inclined plane, which is a relatively easy topic, and I will also introduce an example for this. So let's have a really quick review for what we have learned. So the direct stress equals to P divided by A, and the axial strain is given by the stress divided by the Young's modulus. By combining those two equations, we can have epsilon equals to P divided by AE, and then we consider delta equals to epsilon times L, which means the deformation equals to the axial strain times the original length. Then we will have the change of length or the deformation formula, which is PL divided by EA. Still remember, how did we memorize this formula? L par, right? So just remember, don't write the formula as L par, then that's totally wrong. Okay. So PL divided by EA, L par. Okay. And also for the non-uniform prismatic bars, we will have the formula delta equals to the integral from 0 to L. So L is the length of the bar, right? Then P d z divided by E A z, right? In this chapter, sometimes we will consider P as a function of z sometimes. Firstly, let's talk a little bit about the thermal effect on the axially loaded members. When a piece of material is heated, it will undergo the thermal expansion, and similarly, when a material is cooled, it will undergo the thermal contraction. Therefore, under the change of temperature, we will introduce the thermal strain, which is the axial strain due to the thermal effect. The thermal strain is given by the thermal deformation divided by the original length, so it is rather trivial. But we will introduce a new constant, which is related to the thermal effect, which is alpha. So the alpha is called the thermal expansion coefficient. Therefore, we can say epsilon T, which is a dimensionless quantity, equals to alpha times the change of temperature. That means the axial strain equals to the thermal expansion coefficient times the temperature. Notice that the thermal expansion coefficient has a unit of degree to the power minus 1. So in the later examples, you will see it is look like something like 1.7 times 10 to the minus 7 per degree. So you can see something like that. It is the thermal expansion coefficient. And significantly, after you have this coefficient, you times it with the temperature. Then its unit will become 1, which is the dimensionless form. At the same time, we rewrite the right-hand side of this equality. Then we can find the thermal deformation, which is the axial deformation caused by the change of temperature. It is given by the thermal expansion coefficient times its original length times its change of temperature. So as we just described, when there is a change of temperature on this piece of material, then there will be free expansion or contraction, right? The ball will have the thermal axial strain. Also, the change of temperature can be either positive or negative. Also, we will assume the change of temperature over the entire member is uniform. So we won't say, okay, this tip is very hot, while this tip is very cold. So we don't consider that consideration. So we don't consider that case. So we consider the change of temperature is uniform over the entire beam or the entire bar. Consider a piece of material with both sides clamped now. So instead of letting it expand or contract freely, we will fix both ends so that no matter how, I repeat, no matter how the temperature changes, there will be no change of length over the entire section. So how does it work? So when the piece of material is heated, it will become longer, right? But by applying a force on this end, we can put this elongated bar back to its original length. Similarly, when it is under cooling, when it is contracted, the length of the bar will become shorter. What we do is to apply a force that pulls it back to its original length. So this is the reason why we consider the bar under the clamped condition, because under such condition there will be axial force, axial load, and consequently the axial stress acting in the cross-section of this beam. Consider the case of heating. Well, it is rather similar to cooling, but we just try to understand this case, then we can extend our knowledge to the cooling concepts. So consider this bar is being heated, and there will be positive axial strain, the thermal axial strain. By applying a clamped wall at the end of this bar, it prevents the bar from expansion. However, it will act a compressive load on this bar in order to put this bar to its original position. So we can write the axial strain caused by the clamped end is the negative of the thermal strain. What does that mean? That means the bar is elongated by the thermal expansion, the positive temperature change, right? Then, as I am a clamped end, I must try to push you back, apply a compressive stress on you, right? After you apply the compressive stress, then you will pose a negative axial strain over this entire region. Therefore, we can say the axial strain caused by the external load equals to the negative of the thermal strain. So what is the axial stress caused by the clamped end? We know stress equals to the Young's modulus times the strain. Now the strain is the negative of the thermal strain. Then we will make the substitution. E equals to, so still remember the thermal strain equals to alpha times the change of temperature. Therefore, the stress equals to negative of alpha delta t times E. Similarly, for the axial force, you just times the area of the cross-section over the stress, then you will get minus of alpha delta t E. So those part is completely the same, right? And then you just multiply it by A. So I repeat, the axial stress equals to minus of alpha times delta t times the Young's modulus, while the axial force equals to minus of alpha times delta t times E, and then you times its cross-sectional area. Next, let's move to the statically indeterminate members. Although we can write the equations to solve the unknowns in our previous course, Mechan 2020, by the concept of statics, so those are all what we need to know in statics. However, sometimes it is inadequate, it is not enough to using only those formulas to solve a problem in our course. Therefore, we need to consider the geometry or continuity or other constraints given in the problems. Sometimes we need to apply the principle of superposition. So those things are very hard to explain to you in this stage. You will know what I'm going to talk about in the later examples. Besides, as an engineer, we are aware of the safety in our daily life. Therefore, we need to have some considerations on design regarding to the safety issues. So one very basic thing is that, okay, for example, you have a hook fixed on the wall, right? Then sometimes you may want to hang something on it. Then the engineer or the manufacturer of this hook will say, okay, the maximum load of my hook is 5 kg or 7 kg, something like that. So similarly, in our solid mechanics course, we consider the following safety considerations. First, it is a common sense that the applied stress, you apply a stress on a piece of material, then you should not apply a stress which is too larger than the allowable stress stipulated by the manufacturer, right? So it says 5 kg, so you should get rid of putting 7 kg of material on that hook. Besides, since in our course we talk about deformation frequently, so we will discuss the allowable deformation. So the deformation of a piece of material should be less than the allowable deformation. Well, allowable deformation is often come from the allowable stress, because as we know, allowable deformation is a function of allowable stress. Apart from that, as we have discussed in the previous tutorial, what is the stress that the material will undergo permanent deformation? If the applied stress is larger than a stress called the yield stress, we don't want a piece of material to be destroyed. Therefore, we try to get rid of the material to hold a load which is larger than the yield stress. Therefore, we define the safety factor to be the yield stress divided by the allowable stress, and notice that it should be always greater than 1. That means your allowable stress should never greater than the yield stress of the material. The allowable stress of a piece of material is just rewriting this safety factor formula, which is sigma allowable stress equals to the yield stress divided by the safety factor. We just finished the lecture content for this tutorial. The content for this tutorial, there are not many formula from the lecture. Instead, we have a lot of mathematical manipulations in our examples or problems. So let's try to address a problem. A triple bar linkage is connected as shown. Bar C is welded at the tips of bars A and B. So for those who have attended the industrial training in winter, you should know what is welded. If you didn't attend, let me tell you, it is just like you have a fixed end on those two bars, okay? So after welding, the material is very firmly attached on those two bars. It is not easy to remove it. At the temperature T0, the length of both bars A and B are L0. So this is L0. D0 equals to 1/2 of L0. The thermal expansion coefficients are alpha A and alpha B, where alpha A is less than alpha B. Assume material C has no thermal expansion effect, and the shear stresses on A, B, and C will cause negligible shear strain. That means we don't consider the bending of the material, we only consider the elongation or the axial deformation of the material. Part A. Neglect the direct stress caused by tension of C. Derive the angle of inclination of bar C for small size of data at the temperature T1. T1 equals to T0 plus delta T, where delta T is the change of temperature of the system. I don't know whether it is positive or negative, I just tell you it is delta T. And you have to show that theta, which is the angle of inclination, equals to tangent theta equals to sine theta. Notice that it is just the small angle approximation. For small theta, you have this approximation. And derive theta equals to 2 times alpha B minus alpha A times delta T. Besides, you have to prove the axial strain of bar C related to the thermal expansion coefficients and the temperature. The axial strain of bar C, which you are going to prove, equals to 2 of alpha B minus alpha A squared times the delta T squared divided by 1 minus the numerator. And you are going to find the direct and shear stresses in both A and B caused by the tension in bar C. For this case, approximate the small angle by this formula. Cosine theta equals to 1 minus 1/2 of theta squared for small angles. Besides, we are also going to consider the safety of this structure because I don't want the structure to be harmed. The safety factor of this bar, this linkage, is 1.6. Find the yield stress of this bar if the allowable temperature of this linkage is T1, which is under a change of temperature. Starting from problem 1, firstly we will find what is the length of A and B by using the change of length formula under the axial strain. For this part, we are going to neglect the direct stress caused by tension of C, so I assume there is no direct stress acting on tips of A and B, and we have to derive the angle of inclination of this bar. To do this, we try to consider the change of length formula under the thermal expansion as what we just mentioned. Delta T, which is the thermal deformation, equals to alpha delta T L. L is the original length, where alpha delta T is the thermal strain. Therefore, we can write LA, which is the length of A after the change of temperature, equals to the original length plus the thermal deformation. Similar for LB, it is the original length plus the thermal deformation, which equals to L0 plus alpha A L0 delta T, and for LB it is L0 plus alpha B L0 delta T. By those two equations, we can write the difference of length between bars A and B. Then by small angle approximation, we can find theta equals to sine theta equals to tangent theta. However, we can write tangent theta into LB minus LA divided by D naught. Consider this right angle triangle. This is D naught. Since this bar is inclined, the difference of length between LB and LA will be this opposite side. And then this is your theta. Therefore, tangent theta equals to LB minus LA divided by D naught. Then you substitute this into here, and D naught equals to L naught divided by 2. Then you can show that theta equals to sine theta equals to tangent theta equals to 2 times alpha b minus alpha a times delta t. For part B, we are going to prove the axial strain. Part B is going to prove that the axial strain of the bar C. So we still consider this right angle triangle, D naught and theta. Then this side becomes D naught tangent theta, and the hypotenuse will become D naught divided by cosine theta. If we call this hypotenuse to be LC, then the axial strain of bar C equals to LC minus its original length. So it is the difference or the deformation caused by the change of temperature. It is deformation divided by its original length, which is D naught divided by cosine theta minus D naught over D naught. Then you remove the cosine by multiplying both denominator and the numerator by cosine theta. Then you divide D naught from both denominator and the numerator to get this result. Then by small angle approximation, we find cosine theta equals to this. Finally, we do the substitution to prove the epsilon c formula. Next, we try to calculate the tensile stress and the tensile load in bar C. Notice that we have already got axial strain. Then we can find the tensile stress and tensile load by using the Young's modulus times the axial strain. So this entire piece of stuff is just the axial strain, epsilon c, and then we times it by EC, then it is done. Similarly, for PC, we just times the stress by the cross-sectional area, then you can find this piece of stuff. Basically, you just multiply AC to the stress. Consider at the tip of the bar A, we know for bar C there is a tension like this, right? For this tension, we decompose it into orthogonal components. For the component which is normal to the cross-section, it is the direct force. For the component which is parallel to the cross-section, it is the shear force. Then we can find what is the direct force and the shear force on it. For sine theta is what we did in part 1. It is 2 times alpha b minus alpha a times delta t. Then you put this stuff into the numerator to get the axial force or the direct force. After you get the direct force, then you can find the normal stress by using the direct force times the cross-sectional area, which looks like this. So you just divide the whole piece of thing by the cross-sectional area of A. By similar manner, for the shear force acting on bar A, it is just the axial force in bar C times cosine theta. So cosine theta is what we have found in this part when deriving this formula. And then those two stuff are cancelled out. Then we can have the shear force in this form. Therefore, the shear stress is just the shear force divided by the cross-sectional area. at the tip of bar B, it is rather similar to bar A. One thing we have to change is just the cross-sectional area divided. So I just skip those steps and you can have a look by yourself. Now we consider the safety of this bar because we don't want to harm this bar. We don't want this bar to be permanently deformed by overwhelming load. Now we set the safety factor to be 1.6. Find the yield stress of bar A if the allowable temperature is T1. So what does that mean? First, we have to consider, since you have already allowed this temperature to occur, then there will be allowable stress generated by this temperature. Therefore, at T1, as what we just found in previous part, the allowable stress is in this form that we have already found in previous part. Let me show you. It is here. So now the allowable direct stress is in this form. Therefore, we can find the yield stress by using the safety factor formula, which is 1.6 times the entire piece. The result will become 3.2 alpha b minus alpha a squared times delta t squared divided by 1 minus 2 of alpha b minus alpha a squared delta t squared times EC. So in the exercise problems, I will try to make those quantities in numerical form such that you can calculate it yourself. Next, I'm going to discuss a statically indeterminate problem of the clamped bar. A circular bar ACB of diameter d has a cylindrical hole of length x and the diameter 1/2 of d from A to C. So this is the hole from A to C. It is held between the two rigid supports at A and B. A load P is acting in the middle to the right hand side. Assume E is constant and X is greater than L over 2, so the hole must be longer than 1/2 of the bar. Obtain the formulas for the reactions RA and RB at the two supports due to the load P. Besides, obtain a formula for the displacement delta at the point of load application. You also have to find for what value of X is RB equals to 1.2 of RA. Well, from what you have learned in Mechan 2020 statics, the only formula you can get is RA plus RB equals to minus P, but it makes no sense because you don't know how to find RA and RB by any other things. However, in this course, we are going to introduce you some other equations such that you can find those two reactions. Since A and B are fixed walls, the sum of deformation in sections 1 and 2, so I have already divided this whole bar into two sections in the middle. The sum of deformation is 0 because for this fixed end, when you have a P acting on section AD, that means section AD must be elongated, and consequently, in order to remain the compatibility, the section 2 must be shortened. Therefore, we can write this formula. This is so-called compatibility equation. Next, we find the cross-sectional area of section AC and CB. Notice that the hole is longer than 1/2 of the bar. For section AC, its cross-sectional area is given by 3 pi d squared divided by 16. And for CB, it is 1/4 of pi d squared. Therefore, we can find the area ratio of section AC and CB, which is 3 divided by 4. By those formulas, we continue our analysis. Consider the loading condition on section 1. The axial force in section 1 is RA, but RA is compressive to section 1. Therefore, P1 equals to minus RA. Then, by using the change of length formula, we have change of length of 1 equals to minus RA times L divided by 2E times the area of AC. Similarly, the loading condition in section 2 is in tensile because RB is a tensile force to section 2. However, section 2 consists of 2 segments with different cross-sectional area. Therefore, we have to divide section 2 into those 2 segments and find their change of length respectively. So delta 2 equals to this whole bunch of stuff. From previous slide, we get delta 1 and delta 2. Now we can put them into this compatibility formula. Now we add them together to get this formula, and then do a lot of simplification. Also, we try to eliminate the denominator by using the area ratio relationships. Then we can find RA equals to 2L divided by L plus X times RA. For those steps, I try to skip them, and you should try to understand yourself because it is fundamental to engineers. Now, by integrating those 2 formula, we can solve the system of RA and RB. Then, by a lot of calculation, we find RB and RA. For part B, we have to obtain a formula for the displacement delta at the point of load application. What does that mean? That means when you apply a load here, then you will stretch section AD to the right hand side and compress CD on the right hand side. That means you are going to stretch AD and compress DB. Then there will be a little displacement on the point that you applied the load. Consider the axial strain of section 1. Still, we try to use the alpha formula, and we substitute RA into this formula. Also, we put A1, which equals to 3 divided by 16 pi d squared, into this formula. Then, by a lot of calculation, we can find the delta equals to 8 divided by 3 times P times x plus L divided by x plus 3L times L divided by E pi d squared. For part C, it is rather similar. We just take the result from part A, then solve for this equation. Then we will get the position such that the load of RB equals to 1.2 times RA. Actually, the original problem requires us to also consider the case when x is less than L over 2. However, I wish to leave it as exercise to you because it would be too consuming to do it here. Maybe you can find it in the exercise. Now we change this problem a little bit. The bar is no longer uniform and it will become a tapered bar. The diameter at the left hand side is d, while the diameter on the right hand side is 1/2 of d. Besides, we set that x equals to L over 2, which means this part will become solid. The problem requires us to obtain the RA and RB on the 2 ends due to the load P applied in the middle. Firstly, since the cross-sectional area of this bar is now changing along the length, we need to obtain the equation for that. Firstly, we ignore the hole, that is, at x equals to 0, the diameter of the bar is d. Besides, at x equals to L, that is, at the end B, its diameter will become d over 2. Since the bar is tapered, the diameter of the bar is varying linearly from x equals to 0 to x equals to L. Therefore, we try to find the linear relationship of its diameter by using this method, which has already been taught in your secondary school. Then, you do the simplification to obtain the diameter, which is minus d over 2L times x plus d. Therefore, the cross-sectional area AX without hole is given by this. Notice that this area is the cross-sectional area without hole. Next, we are going to consider the cross-sectional area with hole. By statics, obviously we have RA plus RB equals to minus P. Besides, since we've already found the cross-sectional area without hole, we can get the cross-sectional area for section 1 and 2 respectively. Recall that for section AC, since there is a hole, we consider the cross-sectional area of the hole, which is pi times 1/2 of d squared divided by 4. Then you can write the cross-sectional area of segment AC in terms of x in this form. For section CB, it is rather similar, but there is no hole. Therefore, you don't need to subtract this term from the A prime of x. Therefore, the cross-sectional area for segment CB is like this. Therefore, by considering all what we have got in the previous slide, we can apply the change of length formula to segments 1 and 2. For segment 1, since this time x equals to L over 2, the cross-sectional area for AC is just the cross-sectional area of section 1. We know for section 1, the force acting on it is minus RA because it is compressive. Besides, we take the constant E out. Finally, we put AAC into this integral, which is very complicated. Similarly, for the change of length of segment 2, since there is a tensile force RB acting on it, it should be positive. Besides, we take the E out and substitute our ACB into this integral. Now we use a lot of mathematical techniques to do this integral. For this integral, we first get rid of the denominators, like this, like this. We try to make the denominator of this integral to be a polynomial. To do this, first, we take the common factor out, which is 1/4. Then, we expand all the terms inside the bracket to get this result. Besides, we take out d squared divided by L squared, such that this will become a polynomial. Next, we do a technique to make this part to be complete square, and then we can write the integral in this form. Finally, we let u equals to x minus 2L, then dx equals to du, and we will change the upper and lower limits to be minus 2L and a minus 3L over 2. Then the change of length of segment 1 will become this integral. Then we do the partial fraction for this integral. Since it is the difference of square, we can write it in this way. That is, we factorize the denominator, then write them into the partial fraction form. Eventually, by this form, we can write a times u minus L plus b times u plus L equals to 1. How can we get this system? To get system, we first consider this equation. We expand it to be au plus bu plus minus al plus bl equals to 1. That is, since u is the unknown of this integral, we try to sort all the terms with u and all the terms without u, such that we can write these equations. That means the coefficient of u, which is a plus b, equals to 0, while the constant 1 equals to minus al plus bl, which implies that minus a plus b equals to 1 over L. Then we can solve the system in this way. Eventually, we can write 1 over u squared minus L squared equals to 1 over 2L times 1 over u minus L minus 1 over 2L times 1 over u plus L, which equals to 1 over 2L times 1 plus u minus L minus 1 over u plus L. Then we substitute this result into this integral. Now we integrate this integral such that it will become natural log of u minus L over u plus L. The result will become this, which is pretty complicated. So bear in mind that for example D, it is just giving you some basic ideas about some mathematical concepts to be applied in this problem. So as you can see in previous slides, there are a lot of mathematical concepts that you need to do while solving this problem. But the exact place for the application of solid mechanics concept is not that much. That is, you just apply the solid mechanics method here, and all what you are going to do in the future steps is just to use a lot of mathematical skills in order to solve those displacement out. Now, after we considering the delta 1, now we consider delta 2. Similarly, we put the reaction and the E out from this integral and put our area into it. Similar to delta 1, we take out the common factors such that the remaining stuff in the integral will become a polynomial. Then we let u equals to x minus 2l, then du equals to dx, and we change the upper and lower limits to get this integral. Well, this integral is much easier than what we have just solved for delta 1, right? For this integral, it is rather easy. We just integrate it to get minus of 1 over u, and then you place those two numbers into this result, and then you simplify the whole stuff to get this. To express the answers numerically, it will be 1.698 times RB times L divided by ED squared. Finally, we got delta 1 and delta 2 from previous slides. We used the compatibility equations in order to get the relationship between RA and RB. By substituting delta 1 and the delta 2 into the compatibility equation, we can get these very complicated relationships. Then we get RA equals to 2 divided by 3 natural log 5 minus natural log 3 times RB. Eventually, we relate those two equations. So as you can see, this is for statics, and this is from compatibility. As you can see, for statics, we can obtain an equation very quickly, immediately at the beginning. But for the compatibility equation, we need a lot of time to analyze it, to do a lot of mathematical computations. Eventually, we solve the system to get RB is approximately minus 0.434 of P, while RA equals to minus of 0.566 P. In the previous method, we are mainly dealing with the structure by using the geometry compatibility. Now, we will consider to solve this problem by using the method of superposition. Now, we temporarily remove RB such that this bar has only one force pair, tensile P and RA. Then, for section 1, there will be a tensile load P on it, while for section 2, there is no load acting on it. For section 1, we apply the area of AC, while for section 2, we apply the area of CB. Now, this integral will become 0. Solely consider this integral, we can obtain our results from our previous method. Previously, when we are looking for the delta for section 1, we got this result. Now, we just replace the compressive RA to be the tensile P. That is 8 natural log 5 minus natural log 3 divided by pi times PL divided by ED squared. Now, we remove P and place the RB back. When we put RB back, since RB is tensile to the entire section, we put RB in both integrals for AC and CB. For section CB, which is section 1, we put the area of AC, and for section CB, we just put the area of CB into it. By what we have just found, for section AB, we just put those two results together. Finally, we use the superposition compatibility equation. The deformation caused by P, which is going rightward, right? Plus the deformation due to RB, which is compressive, must be compressive. It should be 0. By combining both the results and the compatibility equation, we do a lot of mathematical calculations such that we can get the result, which is exactly the same to the previous one. In previous example, we dealt with continuously changing bar, which applying this formula. In this formula, AX has a variable X. However, in this case, we are going to deal with another case, delta equals to px dx divided by EA from 0 to L. That is, the force, the direct force inside the bar will become a variable of x, while area will become the constant this time. Let's read this problem. The bar is now rotated in a vertical position. Load P is removed. There is no P inside. Disappeared. The bar is hanging under its own weight. Assume the bar is drilled to the middle. Obtain formulas for the reactions RA and RB and supports A and B respectively. In this case, we can see the area for the two sections are both regular. The area is constant for both sections. However, the P, the tensile or compressive load, will be a variable of x. Firstly, let's still consider this problem in terms of statics. We know that those two reactions are going to support the weight of the whole beam. Therefore, let's try to find the weight of the whole bar. It is given that x equals to L over 2. That means the total volume of the bar is the total volume of the entire bar, which is not drilled, minus the volume of the hole, which is located here. Then, by a series of calculation, we can have the weight of the bar as 7L pi d squared rho g divided by 32. Finally, by statics, we can only get this equation. That is, RA plus RB equals to 7L pi d squared rho g divided by 32. As we know, when x equals to L over 2, this part is solid. Also, the weight of the drilled lower part, that is, for x equals to L over 2, for the material below this level, it is drilled, it is hollow. And for the material above it, it is solid. The weight of the drilled lower part can be calculated in this way, and the result is 3L pi d squared rho g divided by 32. After considering the statics of this entire structure, now we have to consider the solid mechanics part of this problem. The load RB is pulling the bar upward and try to elongate this bar, while the weight inside the bar will compress this bar, so the bar will become shortened because of the weight. So now we conclude that, okay, RB is pulling the bar upward to its original length, while weight itself is tending to compress the bar so that the bar will become shorter. Therefore, we need to consider the deformation caused by each weight independently, which is the method of superposition. First, we remove RB from our analysis, and B will become a free end at this moment. So we completely forget about this, forget about him at this moment. So now this bar has a free end, B, which is here. As we can see, since x equals to L over 2, that means in the middle of this bar, this part will become solid instead of hollow. Next, we consider the cross-section below this level, below L over 2, and above L over 2. For any cross-section below L over 2, all material above this level will compress the material below it, so that there will be negative deformation. That is, the material here will compress this level downward, and there will be compressive load caused by the weight to compress this bar. Now consider what is the weight, what is the load acting on such level of x. We know that the weight of material above this level is given by the weight of the entire bar minus the weight below this level. That is, the weight is the total weight. That is, the compressive load caused by the weight, Wx, equals to the total weight of this bar minus rho g times the volume of the bar below this level. Recall that the cross-sectional area for section AC would be 3 pi d squared divided by 16. Therefore, the compressive load caused by the weight in segment AC expressed in X is given by the total weight of this bar minus rho g times the cross-sectional area times X. So we can treat this part as the volume of material which is below the level of X. And the volume times rho g will be the weight of material below this level. After we do a lot of simplifications and take out the constants out from the expression, we can get the compressive load for any cross-section located at position X in segment AC equals to pi d squared rho g divided by 32 times 7L minus 6S. Similarly, for the interval from L over 2 to L, we can find the compressive load caused by weight for a cross-section at level greater than L over 2, say this one. Then the compressive load caused by the weight in segment CB of this bar will become the total weight divided by the weight of the lower half, which is WL over 2, then further minus the weight of material in this region. The result will be pi d squared rho g divided by 4 times L minus X. Still recall that we have already removed RB, for instance, for our analysis. Now we have the compressive load in sections AC and CB. Now we will account for the deformation caused by weight itself. That is, without RB, the bar will become shortened by its own weight. So what is its magnitude? So we need to calculate it. Notice that the deformation caused by the weight is negative, and it is negative of the compressive load dx times the Young's modulus times the cross-sectional area of AC for 0 to L over 2. So from 0 to L over 2, its cross-sectional area is AAC, and the weight for any cross-sectional area and the compressive load for any cross-section in this section will become WACX. Similarly, for the deformation from L over 2 to L, we have WCB dx divided by E times the cross-sectional area of CB. And then we substitute our results here into this expression. We take out all the possible constants from this integral. Similarly, for this one, put it in. Then we do a lot of cancellations in these constant terms. At the same time, we integrate the linear formula inside the integral to be like this. At the same time, we substitute our lower and upper limits to get the result. We simplify the result in the last page to get that the deformation caused by the weight itself is given by minus of 7 rho GL squared divided by 12E. Next, after we consider the deformation caused by the material weight itself, we will consider the deformation caused by RB. So now we ignore the weight inside the bar and we only consider RB. For RB, it is rather similar to what we just computed. For section from 0 to L over 2, we substitute RB and the AAC into the integral, while for L over 2 to L, we substitute RB and the cross-sectional area will become ACB. Then we take out the constants. We leave RB inside the integral, but you know RB is just constant, and the constant dx will become the subtraction between the upper and lower limits. Then the result will become 14 RBL divided by 3e pi d squared. This is the deformation caused by RB. By integrating the deformation caused by each force, the deformation caused by weight, and the deformation caused by RB, by using the superposition compatibility, which means the deformation caused by the weight plus the deformation caused by RB should be 0 because B is a fixed end, which means the length of the bar is not changed at all. This yields this superposition equation. In another word, to proceed our problem, we just add those two stuff together, which yields this part. Then we do some simplifications to get the reaction at B, which is rho g L pi d squared divided by 8. Finally, we use the equation of statics found previously to get the reaction at A, which is 3 rho d L pi d squared divided by 32. Let's do some closing remark of example 2.2. You should have learned a lot from this example, as there is plenty of calculations involved. In this example, we tried to use two kinds of compatibility to solve the problem. One is the geometry, one is the superposition. Both methods are available to use in your exams or in your daily applications. Depends on which one is easier for you. A and C are more common in our exams, as their calculations are easier, because for D and E there are a lot of integral. Sometimes it is very difficult to set some problems for it. But I can just say, in my offering, in my year, the continuously changing bar is not tested. But I'm not sure whether it will be tested in your offering, so still I recommend you to learn about it. In problem D, the cross-section is changing along x. That is, for the integral, delta equals to p dx e ax. In this case, ax is a function of x. That means you have to integrate this function with respect to x so that you can find the deformation. For problem E, ax, although it's not a function of x, but p is a function of x. So for problem E, you should use this formula. The deformation equals to integration of px dx divided by ea. Actually, in our real life, all those letters inside can be variable of x. For example, the delta, in the most complicated case, will become the integral of px dx divided by ex ax. Yes, sometimes it is very complicated, but in our practice problems, we try to use only one of them to be the variable, such that we can set the problems easier and we can let you solve the problem in a reasonable time. So, in problem E, the axial load becomes the function of x. In another word, notice that for delta equals to PL over EA, the application of this formula has a lot of restrictions. For example, the load should be uniform, which means P should be constant. Besides, the bar should be prismatic, which means we don't accept a bar like this. For this bar, you can also say, okay, the cross-sectional area are the same, but it is not prismatic because, as you can see, there is a ball in the middle. A typical prismatic bar is like this. The bar has a center line for all cross-sections. And also, the cross-sectional area should be uniform, otherwise A will become the function of x and we need to do the integration. And very often, we assume E to be constant. As what we can see, statically indeterminate problems are very often difficult to solve. Just now we solved a statically indeterminate problem by using methods of superposition and geometry. For this problem, we will mainly adopt geometry to solve the problems. First, let's get familiar with this problem. A rigid bar of weight 800 newtons hangs from 3 equally spaced vertical wires. 2 of them is made of steel, while 1 of them is made by aluminum. The wires also support a load P acting on the bar, The diameter of the steel wires is 2 mm and the diameter of the aluminum wire is 4 mm. It is given that the Young's modulus of steel is 210 gigapascal, while the Young's modulus of aluminum is 70 gigapascal. Firstly, we consider if the load is located in the middle, what load can be supported if the allowable stress in the steel wires is 220 milliPascals and that of the aluminum wire is 80 milliPascals. Besides, what is the allowable load if it is positioned at x equals to a divided by 2, which means what if the load is shifted leftward? Besides, we have to repeat this problem by switching two wires such that those three wires are not symmetrically distributed. Now let's consider each problem one by one. Problem A asks us to find the allowable load P of the system. Before we start, we try to analyze the free body diagram of this bar. For this rigid bar, there were 5 forces acting on it, the weight, and 3 forces by the 3 wires. Apart from that, we still have an external load P acting on the system. Firstly, we consider statics because the equations of statics are very easy to find, so we do it first. For force equilibrium, it is significant that the force of the 3 wires equals to the weight plus the external load. While talking about the moment equilibrium, it is also significant. The moment about its center of mass is given by APS2 minus APS1. So we take counterclockwise as positive. This is A. APS2 will generate a positive torque, while APS1 is the negative torque. Well, the sign convention is not that important at this stage. We just want to obtain equations for the relationships between different forces in the wires. So we know this after we considering the moment. Next, we consider the allowable elongation of steel and aluminum wires by taking the change of length formula into account. All the wires will be stretched, but we don't want any of them goes beyond the allowable deformation. So we try to find the allowable deformation of each wire. The allowable elongation of the steel wire is given by PL divided by EA, but you know P is not given in this problem, but we know P divided by A equals to stress. So it will be stress times L divided by Young's modulus, which is 220 milliPascal times 150 millimeters divided by 210 gigapascal. The answer is 0.157 millimeters. Similarly, for aluminum wire, we try to compute its allowable elongation. The result is 0.171 millimeters. However, as what I just mentioned, I don't want any of them go beyond the allowable elongation. Therefore, we will take the elongation of the 3 wires to be the smaller value, which is 0.157 millimeters. Let's find the maximum allowable load for each wire according to those two information we found in previous slide. As we know, the allowable change of length, the allowable deformation is set to be 0.157 millimeters. It is the allowable deformation of steel. Therefore, we also apply this deformation to that of aluminum and the steel. For allowable load of aluminum, P, we change the subject of the deformation formula, delta equals to PL divided by EA. That means P equals to EA delta divided by L. The allowable load for aluminum equals to 70 gigapascal times its cross-sectional area. Recall that those wires are circular in cross-section, times its allowable deformation divided by its original length. Then the allowable load will become 921 newtons. Similarly, we substitute the values into this formula. We know that the Young's modulus of steel is 210 gigapascals, and the cross-sectional area for the steel wires is that small. Finally, we do a lot of calculations to get the allowable load in the steel wire is 691 newtons. After recomputing all those things, we can apply the statics equilibrium. That is, we put all the PA, PS, all the stuff into the formula. Then we can get allowable load on the system, which is 1504 newtons. For the next problem, it changed a little bit. Now P is not located in the middle. It is shifted to the left hand side. For this problem, it will become rather complicated, but significantly, the inclination of this bar would be like this. Consider the statics of the overall system first. From force equilibrium, we have this equation, while for moment equilibrium, we have this. It should be taught in statics and dynamics, so I don't repeat this part. By simplifying those two equations in this system, we can get this system of equations. Besides, there is one thing that we can verify, is that from the first equation, we know that the load in the S1, the first steel wire, is greater than the load in the second steel wire by 1/2 of the applied load. And this inclination verifies this result, that the elongation of the first steel wire will be longer than that of the second steel wire. Now we should consider one thing about the geometry of the system. We know that the bar is rigid. That means this side is always a straight line. We know that the loading for S1 is larger than that of S2. Therefore, we know that the inclination of this bar is like this. It is the original length of the bar, while the elongation of each wire will then be linearly distributed. From this geometry, we can write that the change of length of aluminum wire is the average of change of length of the first steel wire and the second steel wire, which is written as delta A equals to delta S1 plus delta S2 divided by 2. As what we found in part A, the allowable elongation of the steel wire is 0.157 millimeters. In this entire system, the maximum elongation occurs in the first steel wire. Therefore, the load for the first steel wire is selected to be 691 newtons, as found in part A. Now we simplify the system of equation a little bit to get another equation. Notice that now PS1 is known, weight is known. Next, we have known that PS1 equals to 691 newtons. Now we consider the equation of geometry. Then we apply the change of length formula and substitute into each term each change of length of this equation obtained from geometry. And then we simplify the system to be like this. Substituting all our data into this equation, we can have a relationship saying that the load of the aluminum wire is 2/3 of PS1 plus PS2, the load of the two steel wires. Then we do another substitution to get this result. From geometry, we just get this equation. From statics, we have this equation. Combining those two equations will give you the answer of the allowable load, which is 820 newtons. Now we change our problem a little bit, such that the line A and S are switched. Now the two steel wires are located next to each other, while A is located on right hand side. The system loading is shown like this. We want to find the allowable load P under this system if those two wires are switched. Well, it is rather similar. By using statics, we obtain a system of equations. However, in this problem, we are not that sure about the orientation of this rigid bar. I'm not sure whether the rigid bar is inclined like this or like this. It is not that intuitive, so we have to do some reasoning on it. To do this, we consider the change of length formula for S1 and A. For S1, still we use the L-pi equation. We put the values inside, we take the common factor out, and we compare their denominators. Besides, from equation 3, we have PS1 is greater than PA. So compare those two, we will observe that PS1 is greater than PA. Also, the denominator of PS1 is smaller than that of PA. That means the change of length of S1 is greater than that of aluminum wire. That is, delta S1 is greater than delta A. After that, we can confirm that this bar is rotating in this way. Then we have to take the maximum allowable elongation to that of the steels, because, as usual, the steel wire on the left hand side is the one with the largest elongation. Because as steel, the steel wire on the left hand side has the largest elongation. As found in part A, the allowable load in the steel wire is 691 newtons. By geometry, we can write this form. That is, the change of length of S2 is the average of that of S1 and A. Rather similarly, we apply the change of length compatibility and put our change of length formula into this compatibility equation. We simplify this equation and substitute the values into it. We do a lot of calculation and simplifications to get the expression of PS2 in terms of PS1 and PA, while PS1 is a known quantity because it is said to be 691 newtons. Actually, at this moment, we have 3 equations to do. Recall that our ultimate goal is to find a allowable load P. Therefore, for those 3 systems, we solve for P. Do a lot of substitutions and calculations. You will eventually get P equals to 703 newtons. Those things will leave to you as reading. You should read through those steps to understand why you have such answer. You should also mentally prepare for those kind of problems in the exams. It is not easy, and sometimes you need a lot of time to do the computation. Next, let's talk about the stresses on inclined plane. Previously, when we talk about the normal stress, we are often talking about the stress that is acting on a vertical plane. But now, we will consider the stress on an inclined plane, and there are a lot of things that we can do with it. So let's have a look. For this bar, we cut this bar through this line. It is an inclined plane. On this inclined plane, there is an inclined shear force V theta and an inclined direct force F theta. Also, on this inclined plane, there is normal stress sigma theta and a shear stress tau theta acting on it. The cross-sectional area of the vertical cross-sections is A. So, for the inclined surface, the cross-sectional area is given by A divided by cosine theta. So this is A. Then for this inclined surface, the area will become A divided by cosine theta. The normal force and shear force acting on this inclined surface will be F theta equals to the normal stress times the area, while the shear force is given by the shear stress times the area. Still very similar definitions. Now consider this cut piece of stuff. On this piece of material, there is a transverse load P pointing leftward, and for this inclined plane, there are 2 forces, namely V theta and F theta. By statics, we decompose those 2 forces into vertical and horizontal directions. Firstly, we have to know what is theta. For F theta, theta is located here. Notice that don't make the mistake that you put theta here, it is wrong. We derive it by taking this angle as theta. Now consider the horizontal direction. The left hand load P equals to F theta cosine theta plus v theta sine theta. Besides, consider the vertical direction. If theta sine theta minus v theta cosine theta equals to 0, then we substitute those two equations into the system, such that this system has two unknowns. One is sigma theta, one is tau theta. Those two are the unknowns that we are going to solve. Now we replace a theta by using a divided by cosine theta. Then we simplify the system. Besides, we rewrite the system such that we can do some cancellations of the equations. For those two rewritten systems, we adopt 1 minus 2 to get this result. Besides, by this rewritten system, we have the direct stress of the inclined plane. Finally, we can see that we see those two important results. Direct stress on inclined plane is given by p cosine squared theta divided by a, while shear stress on inclined plane is given by p cosine theta sine theta divided by a. We can explore a little bit on those two equations. In solid mechanics applications, we don't want a material to fracture. Therefore, we are rather interested to the maximum direct stress and the maximum shear stress. For maximum direct stress, consider cosine theta in this equation. Its maximum value is 1, which occurs at theta equals to 0. That means, for your bar, if theta equals to 0, that means the surface is vertical. And when you have a load acting on it, then there is load P acting on this surface too. The stress on this vertical surface is P divided by A, which fulfills our expectation and what we have learned previously. Besides, for the maximum shear stress, it is a little bit special. Consider cosine theta times sine theta. Its maximum value is 0.5, occurs at 45 degrees. Therefore, the maximum value of cosine theta sine theta is 0.5, and the maximum shear stress occurs at theta equals to 45 degrees, which is P divided by 2A. Next, let's do the last example of this tutorial. It is drawn from the textbook, but I modified it a little bit. A copper bar with a rectangular cross-section is held without stress between rigid supports. So the initial state is that there is no stress in between the rigid supports. Now the temperature of the bar is decreased by 50 degrees. That means the bar is contracted due to the drop of temperature. Consequently, there will be tensile load acting by the two fixed ends on this bar. Given that the yield stress of this copper bar is 70 milliPascals, find the direct stress in the bar. Show that such temperature, 50 degrees, will cause permanent deformation to the material. Besides, under a safety factor of 1.4, find the allowable drop of temperature and the corresponding stress in the bar. Finally, determine the stresses on all surfaces of the elements A and B, and show the stresses on sketches of the elements. There are also some data given for this problem. For part A, we apply the thermal expansion and contraction formula. Epsilon equals to minus alpha delta T, and we put it into sigma equals to E epsilon, and then we substitute the values into it. Finally, we get that, okay, at a drop of 50 degrees temperature, the tensile stress in the material will become 105 milliPascal, which is much more larger than the yield stress of the material. As what we discussed in previous sections, when a material is under a stress which is beyond its yield stress, the material will undergo plastic deformation, or we so-called permanent deformation. Therefore, it is proved that permanent deformation will occur in this material. Next, we are going to find the allowable stress and the allowable drop of temperature for this bar. Well, for allowable stress, it is rather easy. By using the yield stress divided by the safety factor, we can find the allowable stress as 50 milliPascals. Consequently, we can write this equation, which is temperature-induced axial stress. we substitute the numbers into it, then we can find the allowable change of temperature, which is minus 23.8 degrees. Now we are going to sketch the stresses of some stress elements inside this bar. Under a tensile axial stress of 50 million pascals, for element A, as we can see in the problem, element A is not inclined, it is a very normal element, which is standing very well here. We identify the angle, the theta, for each surface. For vertical surfaces, theta equals to 0. For horizontal surfaces, theta equals to 90 degrees. Therefore, since we know that the maximum direct stress occurs at theta equals to 0, and when theta equals to 90 degrees, there is no direct and shear stress. Therefore, the stresses on element A is sketched like this. For the 0 degree surfaces, there is maximum tensile stress, 15 million pascal acting on it. While for the horizontal surfaces, there is no tensile and no shear stress acting on it. For element B, it is a little bit different. For those two surfaces, their angle of inclination is 45 degrees, while for those two surfaces, their angles of inclination are both negative 45 degrees. By using the above information, we can find the direct stress in the four surfaces. The direct stress for the 45 degree surfaces is given by p cosine squared theta divided by A, while for theta equals to 45 degrees, cosine squared theta equals to 1/2. Therefore, the direct stress in the 45 degree oriented surface is 25 million pascals. Besides, even though we put theta equals to minus 45 degrees into this equation, we can still get cosine squared theta equals to 1/2. Therefore, the direct stress in the minus 45 degree surfaces are also positive 25 million pascals. Next, let's talk about the shear stress. For shear stress, it is not that significant about the sign convention. Therefore, we try to first evaluate one of the shear stresses on those surfaces, then we evaluate the rest of them. First, consider this 45 degree inclined surface. In the derivation of our formula, we know that for an inclined surface with angle of inclination theta, there is a downward shear stress and an outward direct stress. Therefore, let's try to compute the shear stress on this surface. On this surface, the shear stress will attain the maximum, which is p cosine theta sine theta divided by A, reach its maximum. However, we know the maximum value of cosine theta sine theta is just 1/2. Therefore, the shear stress on the 45 degree inclined surface is 25 million pascal pointing downward. Now we have a shear stress which is 25 million pascal on this element. With this shear stress known, we can draw the other three stresses. Since this shear stress is pointing downward, there must be a shear stress which is pointing to this head. You can imagine those two heads are kissing each other, kind of Valentine's Day joke, right? Kiss each other. And also, for the rest of the two surfaces, we have tail to tail, so those two are tail. The tails are pointing to each other, and consequently we have another arrow. Kiss this arrow. Alright, just a kind of Valentine's Day joke for you. So the shear stress is sketched like this. Since we have computed the shear stress on the 45 degree outward surface, which is 25 million pascal, then we know the rest of them are all in magnitude of 25 million pascals. Then that's it. This is how we sketch this stress element. To sketch the shear stress, first you get one of them. Then by using the principle of kissing, or the Valentine's Day joke, then you can sketch the shear stress on a stress element. Let's do a brief summary of this tutorial. Firstly, we discussed the thermal considerations in the axially loaded member. We discussed the thermal expansion coefficient and the change of temperature. Also, we discussed the statically indeterminate problems. We try to find the compatibility equations by using geometry, continuity, and superposition. Besides, we also discussed safety considerations. We talked about the relationship between the yield stress and the allowable stress and the safety factor. Finally, we discussed the stresses in inclined planes as well as the maximum shear stress and the tensile stress. Starting from this tutorial, for each example in each tutorial, I will assign marks for each problem. For exercise 2.1, I assigned 10 marks for part A, 15 marks for part B, and 10 marks for part C. For 2.2, I assigned 20 marks for part A, 10 marks for part B, 5 marks for part C. And since part D and part E are very difficult, I assigned the extra marks on it instead of regular marks. For part E, also extra marks because there are a lot of calculations. For 2.3, I assigned 15 marks for part A, 20 marks for part B, 25 marks for part C. For the last exercise or the example, I assigned 5 marks for part A, 10 marks for part B, and 20 marks for part C. So after watching this tutorial, you should be able to do all those problems independently. In the tutorial video, I might discuss with you some techniques or methods of doing the problems. You can try to do those exercise problems yourself and estimate your final grade on this course. Notice that in this tutorial, there are 165 marks plus 40 extra marks. Notice that those marks and the grade estimate is unofficial, and your final grade depends on your performance in the final exam and the midterm exam, as well as your homework assignments. So bear in mind with that, it is just an estimate. Okay, I am not responsible for the inaccuracy of the estimate. Just try to work out those problems and try to get good marks. And hopefully those reference grades will help you to recognize your ability, to recognize your understanding, your ability, and you can try to work harder on those topics. Okay, this is the end of tutorial 2, analysis of axially loaded members, and hope you like it. Leave some comments below the video to let me know about your concerns. Thanks for watching. See you.